Okay, the probability of wealth, that should be a topic of interest to investors. And we have to talk about probability because investments are, their return is simply not guaranteed. This presentation was made at the Financial Planners Association meeting in Chicago, October of 18. I'm going to quickly review it here. Now, investors' portfolios are characterized by probability distributions, and this has been done for the past 50 years. Here's one shown, and the mean is approximately 0.1 or 10%. And the width of this distribution indicates the uncertainty. And this type of mathematics has been used to model actively and passively managed portfolios. And if this number, the return, is an annual number and the uncertainty represents the annual uncertainty, then this probability distribution is going to drive this investor's wealth after 1 year. What we're interested in is how this portfolio evolves with time over 5 years or 25 years to capture the scenarios that investors would be interested in saving for college, for their children, saving for retirement, etc. Now, there's a lot of misinformation on the internet relative to determining your future wealth because the straightforward compounding equation is often used on the calculators you'll find. And what that compounding equation assumes is that R, the return, is fixed. So the future value is the present value, 1 plus R to the nth power, n is the number of years. This is not valid when R is uncertain and is characterized by a mean and a variance. So given that fact of life, can we still determine an investor's probability of wealth in the presence of annual contributions to make it more practical, and in the presence of annual withdrawals also to make it more practical? Now, Monte Carlo simulations have been used for the last several decades in the world of finance to predict the probability of wealth. And they're very straightforward. If you want to simulate 10 years, let's say, or what the wealth would be in 10 years, you take random values from the probability distribution over those 10 years. And then you do this 1,000 times or 5,000 times, whatever, and you build a probability distribution. They've been used extensively. If you use one of the ones on the internet, you're really not in control of what assumptions have been made for the type of probability distribution. They take a longer time to run, and they're, frankly, I don't think all that intuitive. There is a better way to do it, and that's what we're going to outline in this talk. So we're going to call that simpler way compounding under uncertainty. Also, we'll call it the closed form solution for coming up with what this future probability of wealth is. We're going to start with an initial nest egg, and we're going to use mathematics that's out there and published to see how that nest egg grows with time. And then for each yearly contribution, we're going to treat that yearly contribution as its own nest egg and calculate its growth for the number of years that it's in the portfolio. The math is tedious, but it's well suited to the functionality of Excel. Now you can slow down or stop the video to look at some of the math here in more detail, or look on my LinkedIn page where the paper is outlined in detail. But basically, we're going to use the fact that our future probability is going to be a log normal distribution. When something is distributed as a log normal, this value here is distributed, the log of this value is distributed in a normal fashion. We're going to make use of that fact, combine it with the idea of the Brownian motion of stock prices, and come up with the growth of a nest egg. By the way, when you do that, the return is going to be the geometric rate of return, which is the annual rate of return modified by the effect of the variance and reduced by the effect of the variance, the annual variance of that return. So with some help from Excel, we can come up with the growth of a single, the initial nest egg that the portfolio starts. Gets a little more complicated when we're dealing with the annual contributions. So here we're showing 20 years. The final value of the initial contribution, let's call that SF, that's log normal. So the log of SF is normal. Again, we carefully calculate the growth rates for each of those 20 years. And again, with Excel functionality, that's fairly straightforward to do. It gets a little more complicated when we have to come up with the standard deviation. We're going to use basically for a 20-year situation, a 20-year 20 by 20 matrix to come up with the covariance of all these separate investments and their correlations. Basically, the 19 and the 18-year investments are highly correlated because there's only 1 year when they're not in the same investment vehicle. The 19-year is not very well correlated with the last year's annual contribution, obviously. But the mathematics of modern portfolio theory captures all that, and if you're careful with executing this 20 by 20 matrix, you'll come up with the value for the standard deviation of these yearly contributions. So, does this closed form solution work? Here it is compared to Monte Carlo. We're looking at final value over starting value for the growth of that first nest egg. Excellent correlation, and these were the parameters that we used in this comparison. Also compared it to yearly contributions. So, final value over yearly contribution. Again, excellent correlation between the closed form solution and Monte Carlo. And of, I think, particular interest is when you compare it to historical data, you also get the same skewness and trend that the closed form solution predicts in the actual historical variance of stock prices. So we looked at 20-year holding periods. So a 20-year holding period would be 1925 to 1945, that's one. 1926 to 1946, that's another 20-year holding period. There are 78 of those such holding periods between 1920 and 2018. We bin them, and you can again see that skewness and the prediction of the closed form solution against the historical data. Some 20-year periods, investors were very fortunate, a 12-fold increase in of the final value over the initial. More typically, 2 or 3 fold increase. Now this was for 78. When we did the Monte Carlo simulations, we were talking about 1,000 simulated events. So with only 78, there is more dispersion, but again, the trend of the historical data matches the prediction of the closed form solution. So I built a calculator that captures all this mathematics, and in the output it turned out to be more useful to put the cumulative probability distribution on display. So in this particular case, final value over initial of 10 means that only 20% of the time is it greater than 10. Same data, and it's going to be more convenient to use the cumulative probability distribution. So let's apply this to a college savings scenario. These are all user inputs. So what you believe about the performance of your investments is going to go into the model. So here's the beliefs about performance of equities. Here's a belief about the performance of bonds. Here's whether they're correlated or not. This investor wants $200,000 in 10 years for college education. He's starting with $50,000, saves $7,000 a year towards this goal. And here's his allocation to equities and bonds. Now, what is the probability of this investor succeeding in hitting their goal? And it's only 50%. There is some probability that he will exceed the goal. It's shown here, a 25% probability of it getting up to $250,000, but it's a 50% probability of getting to $200,000. And again, the calculator shows the full distribution of the full probability distribution. Now with this data, the investor can save more, think about student loans, less expensive colleges, whatever, but they're basing their decisions on the actual probability distribution rather than a fixed rate of return, which is not valid and not realistic. Let's look at a retirement scenario. Again, the inputs are all user selected. This investor wants to get to $1 million, starting with $200,000, $5,000 a year. Get there in 20 years. There's their allocation. There's a 46% probability that the goal will not be made. Again, the calculator shows a full distribution, and this investor might not be satisfied with a probability of 46% that the goal will not be made. They can affect that by increasing savings. So let's increase the savings to $10,000 a year. And now there's only a 29% probability that their goal will not be made, or stated more positively, a 71% probability that they will hit their retirement savings goal. And again, the full probability distribution is shown for that analysis. Now, the calculator also works for withdrawals. So let's say the investor is starting with $1 million at the start of their retirement, and they're going to take out $40,000 a year. That's the negative sign. They were a little more conservative on the growth of equities, given just the way they wanted to approach this analysis, and they want to have half their nest egg still available after 20 years. Will they be successful? Actually, there's only a 9% chance that the goal will not be made, or a 91% chance that they will be successful with that withdrawal scenario. And you're probably familiar with the 4% rule, which says you can safely take 4% out a year of your nest egg. This demonstrates the validity of that withdrawal approach. So we all know the nostrum: those who understand compound interest collect it, and those who do not pay it. To this we can add, those who understand compounding under uncertainty can plan for a future consistent with their risk tolerance, and those who do not may be in for an unpleasant surprise. So I recommend that you step up your game in coming up with the probability of your future wealth. This spreadsheet can help you do it. The one I've just gone over, it's available at this hosting site. It's kind of a long URL to type in, but spreadsheetnut.com. This will get you to that calculator. Here's my contact information, and I wish you great luck in your investing future. Thank you.